some basic observations that we can deduce from the circuit of figure 1 are given as the first one is that the both of the SCRs cannot conduct simultaneously. Either S1 will be conducting or S2 will be conducting. Both of these cannot conduct at the same time. The next one is that the load voltage is the same as the source voltage when either SCR is on. The load voltage is 0 when both SCRs are off. And the switch voltage will be 0 when either of the switch will be on, and will be equal to the source voltage when neither is on. The average current in the source and load is 0 if the SCRs are on for equal time intervals, because in half cycle it will be positive and in the other half time it will be negative, so their average will be 0. And we are considering that they are both fired at the same angle alpha and pi plus alpha. So if this alpha is being kept constant for the positive side switch and for the negative side, then in that case the average that we will obtain will be 0. The average current in each SCR is not 0 because of unidirectional SCR current. The current from this switch S1 will be always in positive direction, and from this S2 will be always negative in negative direction. So we can say that the average from this will not be 0, and the average from this S2 switch independently will not be 0. And we have discussed that when we are talking about the RMS current and it is being divided into two equal paths, and they are both conducting for the same time, in that case the RMS from either one path can be calculated by 1 by square root 2 times the current from the total load. For the circuit shown in figure 1, S1 conducts if a gate signal is applied during the positive half cycle of the source. This is my S1, this is conducting in the positive half, and this is S2, it is conducting in negative half. Just as in the case of the SCR in the controlled half wave rectification, S1 conducts until the current in it reaches to 0. So when the current in this switch will reach to 0, in that case this switch S1 will be in reverse bias condition, or it will turn off. And then when this so where actually this circuit differs is that we have an additional switch S2, and it can conduct in negative direction now. In the simple rectification, controlled rectification, we had switches that were conducting in one direction, but now in this case we have two switches that are anti-parallel and can conduct in opposite directions. So therefore when the source is in the negative half cycle, it will be conducting as well. A gate signal is applied to the S2 during the negative half cycle of the source, providing a path for the negative load current. If the gate signal for S2 is a half period later than that of S1, the analysis for the negative half cycle is identical to that of positive half cycle, except the algebraic sign for the voltage and current. So basically what he is saying that if the firing angle alpha is same for the positive half and for the negative half, only that in the case of negative half cycle it will come with a delay of pi plus alpha, and for the positive half cycle it will be 0 plus alpha. So if the value of both these angles is same, in that case the analysis for both these will be similar other than the algebraic sign. For this pi plus alpha, which is S2, its sign will be negative. We are considering that the source voltage is equal to Vm sin omega t. So we saw that when the switch was conducting, in that case the output voltage followed the input voltage. If the switch is conducting from alpha to pi, if the firing angle was kept at alpha for positive half, and for the negative half it was alpha plus pi, so only during these durations my output voltage was I could obtain the output voltage during these time intervals only. Therefore the output voltage is equal to Vm sin omega t during these two intervals, and is 0 for any other value other than these two intervals. The RMS load voltage is determined by taking advantage of the positive and negative symmetry of the voltage waveform. Therefore we can only evaluate it for the half period, and V naught RMS is equal to 1 over pi, and the conduction time is interval is from alpha to pi. So the limits are being put here, and Vm sin omega t whole square. The expression I get in the end is equal to Vm by square root 2 into this quantity. Okay, so in this equation, if you see that if alpha is kept 0, so sine of 0 is 0, this term will also be 0, and alpha by pi will also be equal to 0, and the load voltage is just a sinusoid, and the RMS value is equal to the peak value by square root 2, which is of sinusoid. And if I have the information of the output RMS value of the voltage, then I can easily calculate the output RMS current. I naught RMS is equal to V naught RMS by the resistive load. Now the power factor calculations are. Power factor is equal to the real power delivered to the load by apparent power S. So instead of this apparent power, I can put the Vs RMS and Is RMS, and similarly in place of this real power I can put V naught square RMS by resistance, and by simplifying these two relations I get V naught RMS over Vs RMS. V naught RMS we have calculated in our slide number 9. I'll put that expression over here, and the source voltage is sinusoidal, therefore I can simply put Vm by square root 2, and this is the expression for the power factor. Power factor is equal to 1 minus alpha by pi plus sine 2 alpha by 2 pi. So note that for that power factor is equal to 1 when alpha is 0. If alpha is kept 0, in that case power factor is 1, which is same as for an uncontrolled resistive load, and that the power factor for alpha is greater than 1 is less than 1. So if I keep on increasing my angle alpha, in that case the power factor will keep on getting poor and poor. The average source current is 0 because of the half wave symmetry. The average SCR current is equal to, can be calculated as 1 over 2 pi and its integration from alpha to pi Vm sine of omega t by r. The expression that I get from simplifying this expression is Vm over 2 pi r 1 plus cos alpha. So this expression can be maximum at cos alpha is equal to 0, alpha is equal to 0, so cos 0 is equal to 1. In that case I will get Vm over 2 pi r into 2. And similarly for other values of alpha we can calculate this ISCR average. since each SCR carries one half of the line current